Lecture 2.3, A Brief History of Light. So some of the earliest writings about light by Greek philosophers suggested that they thought that light was something that shot out of the eyes, reached out into the world, touched whatever object you're looking at, and that's the way that we perceive the object. So Empedocles in 400 BC had this notion. We're going to skip ahead to 1600s when Huygens thought of light as a wave phenomenon. So the idea is he realized that light bends around barriers, around small obstacles. So for example, if there's a tiny hole in a barrier right here and you have a light wave shining on it, the light will tend to kind of spread out on the other side, just much as a water wave would diffract through an obstacle. Newton studied light using prisms. He broke white light up by passing it through a prism to separate it into its component monochromatic colors. He thought, though, that light was made of particles. So he had this corpuscular theory of light, where light was made of these tiny little particles, not too surprising, since in his Newtonian mechanics, matter was made of particles. He was more focused on the fact that light appeared to go in straight lines and cast sharp shadows around larger objects. So again, Newton studied how a prism will separate light up into the spectrum of colors from red through violet. Other folks extended this range. So in 1801, William Herschel discovered that if he placed a thermometer out beyond the red end of the spectrum, that the temperature would go up, and it would go up more than if it was actually in the visible part of the spectrum. So by doing this experiment, he discovered infrared radiation, that infrared light is bent through the prism and you can detect it with a thermometer even though your eyes can't see it. Johann Ritter was a German physicist and chemist. He placed different kinds of chemical reactions out past the violet end of the spectrum. If the infrared rays were thought of as heating rays at the time, Ritter was actually looking for cooling rays. So he was expecting that these rays out past violet might cool things down if the things out past red heated things up. So he didn't find that, but he did find that there were rays out past the violet that caused chemical reactions. So he showed that placing silver chloride out past the violet, you could change the color, induce a chemical reaction to change the color. So anyway, he discovered ultraviolet radiation out past the violet end. So by the early 1800s, the notion was that light was probably made of particles because Newton's ideas were the most popular, but that there were these kind of invisible kinds of light rays that were also present. Thomas Young showed pretty conclusively that light was in fact a wave. So in the early 1800s, he conducted experiments with sound and music to study wave properties of sound. He mostly focused on resonance within, like wind instruments and pipes. He then fairly quickly, just a couple years later, extended his work to light. So here are some of the sketches that he made by looking at how light refracts or diffracts through small openings, about how the color changes, about how it separates into different bands. And he made an analogy to some of the similar phenomenon he saw with music and sound. And so he made this musico-optical analogy to argue that light was a wave much like sound. And specifically, he showed that light exhibits interference effects through his famous double slit experiment. So just as a reminder, let's review constructive and destructive interference. If you bring two light waves together that have the same wavelength and that are in phase, so this top wave is going down and then up over one cycle, this bottom one is also going down and then up over one cycle. When you add them together, they'll have twice the amplitude of the individual waves, and you'll have a brighter light. It'll actually be 4 times brighter than either one of them. In destructive interference, the second wave is shifted by 180 degrees or pi radians compared to the first, so that it's going down when the top one is going up. When you add these two waves together, they'll cancel out to 0. You can see that because sine of theta plus pi is equal to negative sine theta. So you basically have sine omega t plus a negative sine omega t, so they cancel out to 0. So when the waves are in phase, they add together. That's called constructive interference. When the waves are 180 degrees out of phase, they cancel each other out, and that's called destructive interference. So here's an example. There's light waves coming in from the left. There's a barrier, and there's 2 openings in the barrier. The light can pass through those 2 openings, and the light from one opening will interfere with the light from the other opening. When you do this, Thomas Young showed that you get these bands of constructive interference and destructive interference. So the constructive interference, you can see there's kind of bright patches where the light adds together, and then in these dark bands, the light is canceling out to have destructive interference. This thing over here on the right is kind of showing what the intensity of light would be like on a card or on a wall where these light waves are striking it. So the way this works is that if you look at a place on a wall behind these 2 openings in the double slit experiment, if the distance from one opening to the spot you're looking at is the same as the distance from the other opening to the spot, then because the waves are arriving in phase at these 2 openings, you'll have the same number of wavelengths along one path as you will the other path. And so when you come over to the edge of the wall, they'll both be in phase. And so you'll get constructive interference at that point. So in this case, the distance, these d1 is equal to d2, or the difference is going to be 0. If you look at a spot at the center of one of these destructive zones, then we've moved up a little bit, and so the path length d2 is going to be slightly larger than the path length d1. So to have a place of destructive interference, this distance d2 must be around a half of a wavelength longer than the distance along d1. So the idea is like you're taking this wave and kind of laying it across this path, taking this wave and laying it across this one. And you can see that at the spot over here is going to be where the end of these 2 guys are. If this path length is a half a wavelength longer than d1, then this one will be going up while this one is going down, and these 2 will cancel each other out. So the criteria for destructive interference is that the path length difference between these 2 paths is going to be a half a wavelength. That's for that first destructive zone. If you move up to the center of this next constructive zone, then now d2 is going to be 1 complete wavelength longer than d1. If you go up to the next one, this path length is going to be 3 halves of a wavelength longer than d1. So now this one is going to be going up while that one's going down. They cancel each other out. You get destructive interference. So in general, when you're at the middle of a constructive interference zone, the criteria is that the path length difference has got to be integer number of wavelengths. If you're in a destructive zone, the difference between the path lengths is going to be 2n plus 1 times lambda over 2. So when n is equal to 1, you'd have 3 halves of a wavelength, and then 5 halves, 7 halves, and so on. So the point is that when Thomas Young passed light through two very closely spaced slits, he saw this pattern of bright and dark zones. And so he interpreted these alternating dark and light zones as constructive and destructive interference, and that supported his view. Well, he used that to argue that light must be a wave because it exhibits this interference effects. So jumping ahead to 1865, James Maxwell, a Scottish physicist, unified work being done in electricity and magnetism over the 1800s into four very elegant equations that describe how electric and magnetic fields are produced and can affect each other. So these are called Maxwell's equations, and they are still widely used today to describe electromagnetic phenomenon. Turns out, so very quickly after Maxwell derived his electromagnetic equations, he showed that in a vacuum, when the charge density is 0 and the current density is 0, he showed that the electromagnetic equations can be written as two wave equations, one for the electric field and one for the magnetic field. So the solutions to these two wave equations are signed terms. Say the electric field would be oscillating, say, along the x direction. The magnetic field would be oscillating, say, along the y direction. So it looks something like this. If this is the electric field oscillating sinusoidally up and down in the x direction, then the magnetic field would be oscillating in the y direction like this. So this is an example of linearly polarized light. He showed that this coefficient out in front here of the Laplacian operator epsilon naught mu naught, that actually sets the speed of the wave as it goes through space. So the speed of this electromagnetic wave is equal to a constant 1 over the square root of mu naught epsilon naught, which just constants that can be measured. So the point is that Maxwell showed that light is an electromagnetic wave, and it also travels at a fixed speed. So it has this fixed speed of 1 over the square root of mu naught epsilon naught. The question is, what is that speed relative to? So if we follow Thomas Young's lead, he made analogies between sound and light to show that light is a wave. Well, if you do the same thing with the speed of sound and the speed of light, you run into trouble. So, so sound waves travel at a fixed speed that depends on the temperature, the mean molecular weight of the gas, and other constants. So, if you have a sound wave traveling through the air, well, the speed of sound is relative to the rest frame of the air in the room. Or if you think about waves propagating along the surface of the ocean, the speed of those waves depends on the acceleration of gravity g, and the depth of the water. So again, this velocity is relative to the water through which the waves propagate. But it wasn't clear what medium is needed for light to propagate. And so in the 19th century, physicists called this hypothetical material the ether. And so they thought that the ether was some substance that pervaded the entire universe and which allowed light to propagate. So if you see light from distant stars or the sun or things in the room, ether must be present in all those different situations. So ether must pervade the entire universe whenever light is like traveling from one point to the other. So there was a quest to try to discover the properties of this ether, which people thought must be there if light acted similarly to sound waves or, say, water waves. In the late 1800s and early 1900s, Albert Michelson, an American physicist, measured the speed of light fairly accurately. So in 1879, he used a rotating mirror apparatus to measure the speed of light to a 0.04% error. So Michelson used this rotating octagonal mirror. So these are 8 mirrored surfaces on this device. This thing spun around at a very high speed. And so light shone on one surface, it reflected off a long ways away. There was a flat mirror, it reflected back, and it struck this other surface to continue on to the viewer. So based on what the deflection of the light is, based on what the rotation speed of the rotating mirror is, you can measure what the speed of light is. So in 1879, this distance here was 2,000 feet. This was conducted in England. In 1926, Michelson repeated the measurement at Mount Wilson here in Southern California. So in this time, that distance was between 2 mountain peaks, which were 11 miles apart. And when he did this measurement, he found the speed of light to be 2.99796 times 10 to the 8th meters per second, which was 0.01 with a 0.01% error. The current definition is given by this: 299,792,458 meters per second, and in fact, this is now a definition. So lengths and time are actually derived from this definition of the speed of light. So c is now defined to be this value exactly. So it's because this happened in our own backyard, it's worth pointing out. So Mount Wilson Observatory is where he set up the rotating mirror. This is in the mountains above Pasadena. The flat mirror was located on a mountaintop near Mount Baldy. So University of La Verne is right here. They shot the light beam from Mount Wilson across the San Gabriel Mountains. It reflected off this mirror in Mount Baldy and then came back. And that's where he made the 1926 measurement. So here's what's left of it today. This is the peak, mountain peak at Mount Baldy, and you can still see the kind of the concrete piers that were used to hold the mirror that was to reflect the light from Mount Wilson, which you can see over on the horizon there. Okay, anyway, just kind of neat because this is right in our own backyard, so a little bit of history there. So at the end of the 1800s, physicists knew that light was a wave. They knew that it was an electromagnetic wave. They measured the speed very precisely, but they were still on the hunt for this hypothetical substance, the ether, that through which they thought that light propagates. So in the next lecture, we'll talk about the Michelson-Morley experiment, which surprisingly showed that the ether does not exist. And this is going to lead into the development of special relativity.